Okay, let's talk a moment about fusion. Fusion is where you take two smaller nuclei, and when they actually combine, they combine a larger, heavier element. So that's what fusion is. The example I'm giving you is basically between deuterium, hydrogen 2, and tritium, hydrogen 3. And when they're combined in a nuclear fusion reaction, they form helium and a neutron. Now the reason I highlighted this one in particular is the lowest temperature that this reaction can occur is 40 million degrees Kelvin. So that's why we call them thermonuclear reactions. And while we do talk about the fact that if we had fusion as something to produce energy, it would actually have less harmful byproducts. At the moment, when we do actually have thermonuclear reactions occurring, either it's for a hydrogen bomb, or the amount of product that we form, the amount of reactants we form, the energy that's produced is actually less than the amount of energy that's required to contain it and not let it go uncontrolled. Okay? In the sun, if you look at the sun before the sun becomes a red giant, what happens is on the surface, remember we have fusion where hydrogen is being converted to helium. And don't forget, that's how we determined the element helium. It was the astronomers that looked at the sun's absorption spectrum and identified helium as the new element. In a lower level, when all the hydrogen has been used up, you start seeing that helium under higher pressures and temperatures gets fused and forms carbon and oxygen. This occurs, okay, in the interior. And then, as we go under higher pressures, then the heavier elements are being formed, and that's neon to sulfur. So those are being formed. And at the very center, at the core of the sun, that's our iron-56 core. And the iron-56, as you recall with our nuclear binding energy, that's the most stable nucleus. And that's actually why our core tends to be iron-56. Okay, so now that we have an idea about fusion, let's move on. And this will be rather quick. What we just want to do is mention a few terms about the biological relevance. Okay, so first of all, when we talk about radiation, we have two types. We call them ionizing and non-ionizing. Well, as you can tell, ionizing means that that radiation produces ions. So let me give you an example. Okay? When ionizing radiation, which in that would include alpha radiation, gamma radiation, and beta radiation. Okay? What would happen is you could have water, it gets ionized, and so basically you lose an electron. That's my ionizing radiation. When this happens, it reacts with another water. Okay? And what it does, it produces my hydronium ion plus a hydroxide radical. And this is very reactive. Okay? So that's non-ionizing, doesn't do this. Okay? For the ionizing, the production of hydroxide radicals is what makes it so dangerous, because basically it's a hydroxide radical that starts basically reacting with all the different chemicals in your body. Okay? Let's talk about some terms now. When we talk about radiation doses, we have two terms that we usually use. The gray, which is our SI unit, and that's equivalent to 1 joule of energy per kilogram of tissue. Okay? Another term is called rad. Okay? And that is the radiation absorbed dose. Okay? And it corresponds to 1 times 10 to the minus 2 joules per kilogram of tissue. Okay? So that doesn't seem so bad. Okay? And what we need to keep in mind is that depending on the type of radiation, this 1 gray may be more seriously affecting, more serious to your system with one type of radiation versus 1 gray of another type. So we also need to take into account the effectiveness, the relative biological effectiveness. Okay, so let's mention that. So, since not all radiation, okay, is equally harmful, we need basically a scaling factor, and that scaling factor is called RBE, the relative, I can spell today, the relative biological effectiveness. Okay, so when we talk about that, it's 1, approximately 1 for beta, and gamma is approximately 10 for alpha. Well, why is it so large for alpha, considering that alpha particles get stopped at the skin tissue? Because don't forget, if you actually absorbed, like you consumed alpha particles, because they are so heavy, being a helium nucleus, that the bottom line is they can affect much more damage than the beta or gamma. And that's why the RBE is so large. So what we do is with the scaling factor, we talk about it as the effective dosage. So with this scaling factor, now we can use REM and not the band REM. REMS. And REM stands for the Rankine equivalent. Oop, I can't spell today. Equivalent in man. Okay, so let's go ahead and just kind of give you an idea about REMs and how we're affected when we are irradiated. So, if our dose in REM is 0 to 25, there is no detectable effect. Okay, from 25 to 50, you're going to have a slight temporary decrease. Temporary. I can't spell again. Temporary decrease in their white blood cell count. Okay. So, all right. If I go from 100 to 200, these are when these patients exhibit nausea, and a marked decrease. Okay, a marked decrease in your white blood cell count. And if you're 500, if you have a population that's been exposed to 500, okay, REMS, all right, we're talking about acute. These are short-term effects. You have death of half the population. In 30 days. Okay, so these effects are short-term. Okay, so the bottom line is that long-term, when you're constantly exposed, the effects, your dosages may not necessarily be as high. You might be long-term, lower exposure. So you can see this marked decrease in white blood cell count. So what's happening here? So when you're actually affected by your radiation with these dosages, you're going to notice really the effects on your more rapidly dividing cells first. Because remember, we're talking about primarily ionizing radiation. So any of those hydroxide radicals, wherever they are formed, and they're formed in water, you know that's a huge percentage of our body. The bottom line is that you're going to have a lot of damage to our DNA. And so as you're rapidly, basically dividing and replicating your cells, then your daughter cells, any damage that's done, will be seen more quickly with any types of cells that rapidly divide. So one, our white blood cells, okay, it's about a 3-month turnaround for red blood cells, but our white blood cells also, we get a much shorter turnaround. Also, the nausea, because basically our skin, okay, so the endothelial cells, those will be affected more rapidly. That's why we see hair loss when people are exposed to a lot of radiation, because those cells would show you the first effects. Okay, so that's the end of our chapter on nuclear chemistry, and we'll start on the next subject shortly thereafter.